Greetings of the day to all of you. I welcome you all to the 11th lecture on modern power electronics. The last 10 lectures were conducted in an offline classroom environment, but unfortunately, due to the COVID pandemic getting worse, we are moving back to the online mode of teaching. So we resume with our 11th lecture, which is going to be on inductor design. In the last few lectures, we had been discussing module 2, which was encompassing different aspects of design in power electronic circuits. We started off with the design of gate driver circuits, optical isolators, bootstrap circuits. We then moved on to discussing about snubber design, how we design turn-on snubbers and turn-off snubbers. And then we also discussed the design of heat sinks, where basically we try to model thermal dissipation as an electrical circuit through thermal resistances, which are not electrical resistances but which basically measure the capacity of any element to shed off temperature or to propagate power loss by means of heat dissipation. And finally, we discussed about inductor design in the last lecture, where we discussed that in an inductor, or whenever we are trying to design an inductor, our main aim is to get the maximum value of inductance or store the maximum amount of energy in the form of a magnetic field in the smallest amount of space. And that is precisely why we use ferromagnetic cores over which we wind our inductors. These cores can be rectangular in nature, or they can be spherical in nature. So you wind the winding on a limb through some n number of turns, and there is a current I flowing in the circuit. So you produce some MMF Ni, which causes the flux to flow, and you provide a closed path for that flux. So this is a winding, and then there is a closed path for flux to flow. So flux is the result or the effect in the circuit, and the opposition to the flow of flux is the reluctance. So these cores offer very low reluctance path, but because they offer low reluctance path, it also means that these cores can saturate at very small values of currents flowing through them. To prevent saturation, we often introduce a small air gap within the cores itself. So the flux has to pass through air, which overall increases the effective reluctance of the circuit, and therefore controls or prevents saturation of the core. So generally we have a controllable air gap. The length of the air gap can be better controlled if we use E-type cores. So we have E-type cores, and then we push together two E-type cores like this. So you have a cylinder known as a bobbin, which is a hollow cylinder generally made up of plastic. So it is hollow, and over this bobbin we wind our copper winding, and then the E protrusions, the middle limbs of the E-type core, are pushed into the bobbin like this in the hollow part of the bobbin. So the bobbin stays over this middle limb, and that's where your winding is done. And we have also discussed that how deeper you push these two E-type limbs into the bobbin, by that you will also control the length of the air gap on the left hand side and the right hand side. This is one benefit of the E-type core. The other benefit is you are also splitting the flux path, right? So within the same core material you will get more path for electrical flux. And your entire goal again is to minimize the area of your core, get maximum possible inductance within smallest possible area, or maximum storage of energy in the form of magnetic field, again with the smallest possible area. That's why you do it by restricting the path of flux within the core, within a high permeability, low reluctance path. Now, in the last class, when we were discussing all the magnetics associated with inductor design, we came across an equation which was the first equation of inductor design, you can say L square is equal to L is equal to N square upon effective reluctance of a circuit. So reluctance of any limb is simply equal to L, the length through which the flux flows, upon mu upon A, let's call it AC, or area of cross section of the core. Now if you have many limbs of the core, then of course these reluctances will add up in series, parallels, whichever combinations, and they will give you an effective reluctance. So sometimes a core may be designed in such a way that you may have split up split up reluctances, and you will have to find an effective reluctance in order to find the inductance. So all this we have discussed till now, which was the properties of the core, such as reluctance, and how the length of the core or the area of cross section of the core affect the reluctance, and how we are trying to basically miniaturize the size of our inductor and maximize our energy storage capabilities. But when we design an inductor, it's not just the value of inductance that we desire. So if I tell you I need to design an inductance of say 3 millihenry, that is not the only information I need. Many times I may also require the information of the maximum current that can flow through my inductor without causing the core to saturate. So when I'm designing an inductor, I may design an inductor of value 3 millihenry such that the inductor allows a maximum current of say 10 ampere without saturating the core. So this is another constraint of inductor design, that is core saturation. Now I know that for an inductor the basic equation is Ni is equal to phi into effective reluctance. The cursive R here represents the reluctance. Now of course the effective reluctance, especially if you have multiple limbs or air gaps within them, then you will definitely need the effective reluctance. I can also call this as B into area of cross section of the core. AC represents the core cross section area into effective reluctance. Now whenever I choose a core, in the data sheet it generally mentions a maximum flux density, or magnetic field strength as you may call it, B max, and corresponding to a B max there will always be some I max, and this gives me the second constraint. This equation gives me the second constraint, that is Ni max is equal to B max AC into effective reluctance. Again, I told you, whenever in the previous lecture also I had told you that whenever you try to get maximum flux density within a small area, you also reduce the current carrying capability of the inductor. So air core inductors can carry large currents without getting saturated. However, with ferromagnetic cores, like ferrite cores especially, or iron cores, these kind of cores tend to saturate at small values of current, even though they allow very high Bmax, right? Because the area of the core, when you're trying to reduce the area of the core, you are also reducing the maximum current carrying capability of the core. Of course, if you change the effective reluctance, if you somehow increase the effective reluctance, it will also help you in increasing the maximum current that can be tolerated by the core without going into saturation. So this equation that I have is basically giving me a constraint on controlling the saturation of the core, the current at which my core will saturate, right, which will correspond to a Bmax value that is given in the data sheet of the core itself. So this is the second constraint. The third constraint that we have is a physical dimensional constraint. Suppose you have a core like this, let's assume a rectangular core, right? And if I cut through that core, of course it's a limb, and there are, it has been wound. If I cut through that core, I will see my conductor cross sections like this, right? So if there are n number of turns, this will be my conductor cross sections. Each conductor cross section will have some area, so that is, let's call it area of the winding, right? So AW is the area of the winding, and if you have n number of turns, the total area occupied will be n times AW, right? Sometimes you may not just have single winding, but you will wind it once, and then you will increase the number of turns by winding over those turns. So in that case, you can have multiple conductors, packed like this to increase the number of turns over the same limb. Of course, they will be existing over this side also, right? Something like this, so on and so forth. So this is a cross section of the core along with the conductor that I have cut, and this area is the area occupied by the conductor, not the core, but the conductor. So this is the area of cross section of the wire or the winding, and total number of turns, that gives you the total area occupied by the conductor. Now the physical constraint says, so this is a physical constraint. It says that the total available area within the core, this area, this is known as, this inner rectangle, the space in which you will wind the inductor, this space is known as the window area. Now it is obvious that the window area should be greater than or equal to n times AW, which is the area occupied by the conductor. That is obvious because you have to wind the inductor without exceeding the space that is available for the inductor to be wound. So this is the window area, that is the area of the core, right? Space within the core where you have to wind the inductor. And then this is AW, is the area of cross section of the wire or the winding which you are using to wind over the inductor, wind over the core, and n is the number of turns, right? So NAW is this area occupied by the conductor, and window area is the area that is available for the core to be for the inductor to be wound within. Now this constraint is very obvious, that this should be greater than or equal to the conductor area. However, it is known that if this is your window area, all of this area is not generally available for you to wind the inductor. I mean, you cannot wind all of this WA with the inductor. Only some part of this total WA window area can be filled in by the conductor wires, and that gives us another factor. Let's call it KW. This is known as the window fill factor, or it is also known as window utilization factor. And of course, KW is less than 1. It can be anything between 0.5, 0.8 to 0.8. Now, why is the entire, window area not available for you to wind the conductor? Because there is some area occupied by the insulation of these windings, right? There is some area occupied by the bobbin, if you have a bobbin over here, right? So some area is occupied by the bobbin. There is some area that is occupied by the packing, the natural packing of these circular cross sections within a rectangular structure. So if you have a rectangular structure, even if you pack circular cross sections as close as possible, you will always have still some space left, right? Even if you pack them as closely as possible, this right? So these spaces that will naturally occur between circular packed holes structures within a rectangular frame, this will also reduce the effective utilization of the area. So that is why we cannot utilize the window area completely, because we cannot fill the entire area with the conductor, because the conductor is circular. It is bound to leave some spaces in the middle. Also the conductor will have some insulation, which will also occupy some space. The bobbin will occupy some space, and all these factors together reduce the effective window area by some factor, which is termed as the window fill factor or the window utilization factor. So this is a constraint on the space. Now this is the third constraint that we have. And the last constraint that we have while designing an inductor is the copper loss. So okay, I want an inductor with some value, with some maximum current that it should allow without saturating. Also of course, while winding the inductor, मैं इतनी winding ना लगा लूँ कि मैं core के size से ही बाहर चली जाऊँ. There's no space for me to wind the core, so I have to take care of that also. And also sometimes I have to take care of the copper loss, that even while I'm winding an inductor, the effective resistance of that conductor which I'm winding over the core, it should not be so high that there is too much of copper loss. So generally I also tend to control the resistance of the winding, and we know that the resistance of the winding is simply equal to rho L by A. Right? Now what is this L and what is this A? Till now the L that we were discussing in the last class, that was related to reluctance, that was the length that was traversed within the core by the flux. This length is the length of the wire which we are winding over the core, and this area is the area of cross section of the winding, which is the same as AW. So I hope you do not confuse yourself between various areas. This is area of cross section of the core. This is area of cross section of the winding or the wire, which is used here as well as here. And this length over here is the total length of the wire that we are winding over the core. If the wire has n number of turns and there is length per turn is given, then I can simply use it as this, where LT is length per turn, and simply multiply it into number of turns, it is the total length, right? So the fourth constraint is a constraint on the resistance of the wire, because this resistance is actually going to control the copper loss in the circuit, which I know is going to be the RMS value of the current flowing through this inductor into the resistance of this inductor. And generally, to control the copper loss, I will try to control the resistance by means of this equation. So I now have, in the design of an inductor, I now have 4 constraints. One constraint is the value of inductance that I want. The second constraint is the maximum current that my inductor can tolerate without my core getting saturated. The third constraint is a spatial or a dimensional constraint, that the amount of conductor that I'm winding over the core should not exceed the window area of the core. And the fourth constraint is a constraint on copper losses, which helps me choose a value of resistance of the winding that is being wound over the core that does not cause too much copper losses. Okay, so all these 4 constraints, I want to combine them together to get a design equation. Let's start with the third equation. So I have WA is greater than equal to N, I take KW down, into AW, and I substitute equation 4th into equation 3 to replace winding, the cross section of the winding. Okay, so I get rho length per turn into number of turns divided by R, where R is the effective resistance of the wire, not the reluctance. Okay, I'm using capital cursive R for reluctance. Fine, so I can write this as N square, and this goes off. What I basically want to do is I have chosen the number of turns depending upon the value of inductance like we did in the last class. I want to choose the dimensions of my core. So all those parameters which are related to the dimensions of the core, I'll bring them on the left hand side. This is the winding window area. So the area, this is my core, this is the area enclosed by the core, this area. So of course it is a function of the dimensions of the core. Therefore it remains on the left hand side. What else remains on the left hand side is the length per turn. Okay, now this is my core and I am winding a wire over this core. The length per turn of the wire will depend on the dimensions thickness of the core itself. How thick is this? The perimeter of this limb will decide the length per turn, right? So the length per turn is again a function of the core dimensions. Therefore, I am going to get the length per turn over here on the left hand side. I want to replace a number of turns, so I'll use equation 1 in this equation. I can write n square as L into R reluctance effective. So this equation substituted here into rho by kW into R. Now I can also substitute effective reluctance by the second equation. I have incorporated this. I started off with this. I have also incorporated this. Now let me incorporate the second constraint, which is, I'll substitute for R effective. I can write it as WA by LT is greater than equal to L rho KWR. R is a resistance. R effective is the effective reluctance into N I max upon B max, and this is AC, area of cross section of the core. I can again write this N as N square by N. Okay, and I simply just multiplied and divided by N, and I can rearrange this equation as WA by LT greater than or equal to L rho by N KW resistance. N square is L effective. I'm again using this equation. L into R effective. So L square into R effective, right? Into I max upon B max into AC. Again R effective, I will use this equation again. So R effective will become I max by B max. So I max square, B max square, and by AC, AC square, and into N, right? This N and this N will go. So I will get a design equation from all these four equations I have combined. All the four constraints I have combined into one equation, which is my design equation for the inductor, and that is window area upon length per turn, which is again a function of the size of the area, should be greater than or equal to L square resistivity of the wire that you are using, value of the inductance that you want squared, resistivity of the wire that you are using, R effective तो हमने replace किया था, into maximum current that my core should be able to tolerate squared divided by kW, the resistance that you want in the wire, which will come out from the copper loss of the wire, the maximum core flux density that the data sheet will give you, into AC square. AC is the area of cross section of the core, so I'll also take it here, AC square. So all these things on the left hand side, they are basically giving me dimensions of the core. This is window area, this is area of cross section of the core, this is length per unit turn, which will again depend upon the perimeter of the limb over which I am winding my my wire or my inductor winding. So obviously if the perimeter, if this area is say, suppose this is the central limb, and if it is very thick, then obviously the length per turn is going to be large. So the core dimensions are going to affect length per turn as well. Now we have basically manipulated this equation in such a way so that I can incorporate all my design constraints within one equation. I can choose the value of inductance. I can choose the maximum current that the core should tolerate without going into saturation. I should be able to choose the maximum value of resistance that that the wire should have, and accordingly I will choose a core with certain set dimensions, its core area, its window area, its length per unit turn. This will come from the data sheet, resistivity of the material, whether it's copper winding that you're using or whichever winding you're using. So this is putting all the constraints together in one equation. So this particular thing, all the geometrical constants of the core, they are clubbed together as a constant called as core geometrical factor, kg, which basically it describes the effective electrical size of the magnetic cores. So effective electrical size is depending upon what are the electrical quantities, different electrical quantities, what will be the size of the core that you have to choose. So when you have when you want to select a core, you take a data sheet and you check if this particular combination, this square into this exceeds the values that you want, and then that's how you choose the dimensions of your core. It also tells you some interesting things, this equation. The first thing that it tells you is that if you want to use a small core, basically that's what your goal is, to miniaturize your core to get the biggest possible inductance in the smallest possible space. So if you want to make it small, then you will have to increase Bmax, right? That means you have to use a core that has high flux density, or that allows greater flux to pass through it, which has high permeability, low reluctance, whatever you may call it. So that way you can make your core smaller. Or you can also make your core smaller by choosing cores that can have small Imax. And I told you previously also that these two are generally common. That is, if you take a ferrite core, it has very high flux density, maximum flux density. It has a curve like this, very tall and narrow BH curves. So this it can tolerate very high value of B, but then it will saturate at very small amount of current. So small current, high B, this core is definitely going to have a small area. But the problem with this core is that it will saturate at small values of current. You cannot cause a large value of current to flow through the windings of the inductor in this case. And if you want that to happen, then of course you will have to increase the reluctance, tabhi jaake zyada current it will tolerate. Another way of miniaturizing the core is to allow greater losses in the core. Let there be more effective resistance of the winding. Then in that case also you can effectively reduce the size of the core. So all these will give you insights on what to increase and what to reduce in order to get the optimum size of the core. So for sizing of the core, this is the general equation that you tend to use, and we generally match data sheets. You take a data sheet, you check its core dimensions, you check the window area, you can easily calculate it from the dimensions given, and then you see if this particular quantity is greater than, you know, all of these quantities that you want, depending upon your I max, depending upon the B max of the core. And that's how you know, you choose the size of your core. Of course, it has to be just slightly greater than or equal to this. You don't tend to make it too greater, otherwise you're increasing the core area too much. So this is a design aspect of cores, where we are also considering other factors such as copper losses, such as maximum current at which it saturates, and the other thing that we discussed was, of course, the inductor value as well. You're considering that also, and then the physical constraint of, you know, fitting the conductor material within the window area of the core. So based on these four constraints, you come together with one design equation, that is this particular equation. Maybe we should take up a data sheet and I can share a data sheet with you, and you can try to design cores and design inductors on the basis of that. So that was about inductor design. I hope it is clear. If you have any doubts, please feel free to contact me. We can have a doubt clearing session later in the week after we have a couple more lectures. That's all for today. Thank you very much.